Hello and welcome. I am here to give you a quick walkthrough of the solution to my 2025 Excel challenge that I shared last week, which I described as a bit of an Excel challenge, a bit of a computer science challenge, and a bit of a math challenge to parse this crazy formula to try to figure out what was going on. Now, I think people approach this a few different ways. I'm going to talk a little bit about the three main ways that I'm aware of. And obviously I'll mention the people who got it right and the lucky winner of the ticket at the end. But I'm going to start from the sort of most abstract and then work my way down to the most sort of backward engineering approaches. So starting from the very abstract, let's just look at this. We won't be doing any computery stuff. This is just going to be a sort of theoretical exercise. So let's start by looking at this WH expression. And as you'll see as I talk through this, I suspect some people figured this out. It was probably a little not obvious if you didn't know what you were looking for, but these two-letter variable names were subtle, but they were hints. And so the WH here, the hint was that this is a function for creating a while loop. But let's just for a minute say we don't know that. So we've got a function that takes 5 different arguments, RICOS. And what's going on? Well, the first thing you'll notice is that C is a function because we're calling C as C of I here. O is a function because we're calling O of I here. R is a function because we're calling R with a bunch of other stuff here. And then S is also a function. So we've got a function with 5 different arguments, 4 of which are also functions. And if you look at any time that this function actually gets called, you will see that the first argument of the function is always the function itself, and that you might be familiar with that already. That's just the sort of the overhead required to use a recursive function in Excel without putting it in the name manager. So this, R here and R here and R here all end up just being WH. So what is going on here? We're saying if some condition is met, a condition that's a function of the input, then give us an output function that's again a function of the input. Otherwise, make a recursive call, which in the actual use is going to be a recursive call back to the same WH function with the same R, the same C, the same O, the same S, but with some S function applied to this I. So what does this mean in practice? It means we're going to apply the function S to the input I over and over and over again until this condition C is met, and then we're going to give an output. And that is, very much, that is the sort of definition of a while loop. We're going to take some action over and over and over again until some stopping condition is met, and then give some output. So now that we understand that in principle, well, a couple of things. One is that might help you to look at some of the rest of the code and see it not just as a bunch of random individual things, but as some collections. So again, note that R just ends up being a recursive call back to WH. So there's really 3 functions to build a while loop here. There's the stopping condition, there's the output, and then there's the step from one step of the input to the next. And if you look here at the names, you'll see here we've got an SC, SO, and SS that all get called in an SF. So here's your SC, SO, and SS, just like the original COS inputs to that function. So here we've got a stopping condition, an output, and a step, all related to an S function that then all get called together on the S function. So can we figure out what this S function is doing? Well, let's break it down bit by bit. First of all, when it first gets called, it's got 2 inputs, I and J, and we're going to stack them together, and that is our input to the recursive call. Okay, so what is the stopping condition? It's that xi2 is equal to 0. Okay, so now we've got to understand the ex function quickly. So again, takes 2 arguments, I and j, and it returns index ij. So here, I is our input, which we know at least at the start, that is, it's 2 values stacked together. And so x of I2 just means the second argument. So if we're stacking I and j next to each other, the second argument is just j. So the stopping condition is we've got a pair of values, we're going to do something to them, and the stopping condition is when the second value is 0, we're going to stop. Okay, so what's our output? Our output is just at I, which just gives us the first value of I. So we're going to do something to this pair of values until the second one is 0, and then we're going to return the first one. Okay, pretty clear. So now what's the step that we take? The step is subtract 1 from I. And important to know that if I, in this case, is a sort of pair of values stacked together, then this minus 1 will lift over both of them. So we're going to start off with the values I and j. Then we're going to, if j is not 0, we're going to subtract 1 from both of them. So we'll get I minus 1, j minus 1. If the second argument is still not 0, we'll keep subtracting. So we'll subtract until we've subtracted j times, at which point we'll have I minus j, and j minus j is 0. And then we meet this condition here that the second argument is 0, and then we output the first value. So what do we end up with? We end up with I minus j. So this whole thing from SC down to SF is just a very elaborate way of building a subtraction function. We give it two numbers, and we end up with the first number minus the second number. So you can see that there is a good amount of obfuscation going on here. So let's start by just cleaning all this up. Get rid of everything to do with the subtraction function. And here, where we say SF of these two values, I'm going to get rid of that bracket and that bracket, oops, sorry, and this bracket, and just say that value minus that value. And is there anywhere else? I think that's the only place we used SF. Okay, good. So now it looks a little bit more sensible. And now we can pretty quickly see there's the same pattern here. We've got GC, GO, and GS, and then we've got a GF. So we've got a function G, and same pattern as before, that is calling the while loop on two inputs, I and j, and we've got a G condition, a G output, and a G step. So again, let's take a look at those. So first of all, the input that we're operating on is again a pair of values. So our G stopping condition is again that the second value is equal to 0, and our output is the first value. So we're going to do something to the pair until the second value is 0, and then we're going to output the first value. Now this is where it goes from a little bit goes from being a sort of pure computer sciencey problem into being a little bit more of a mathsy problem to be able to understand at the last step. So what is the step that G is taking? Well, as you can see, a little bit more complicated, but start with the basics. We know that the input is just a pair of values, a pair of numbers. Well, I guess we don't technically know at this point it's a pair of numbers. I'm inferring that from down here, but since we're doing, subtraction operations on them, I'm going to say comfortable in saying that it's a pair of values. I'm going to shrink this up a little now, I guess. So what are we saying? We're saying we're going to sort something, which is this array, and we're going to sort it by the first index in descending order, and we're going to sort by column. So which makes sense because there are no rows. There's only one row. So if we sort on the first row in descending order, it just means we're going to sort them so that the biggest one is. I'm trying to figure out which way around you guys are going to be seeing my hands mirrored, but I can't figure it out. So anyway, we've got the larger value is going to come first, or first, not sure, and the smaller value is going to come second after the sort. So what values are we stacking together? Well, the second value is just the second value from the previous input. So if we start off with I and j, then we're going to end up with something and j before we sort. And what do we have over here? We have the first value minus the second value. Now here it would be helpful to see where we first call this. Can we deduce anything useful from that? Where is it? Oh yeah, so the GF goes into the CF, and the CF gets called on first and second elements of this thing, which is, yes, starting off as, all right, so I'm going to jump ahead a little bit. So we've got the same pattern again down here. We've got a P function for which we have three functions to build up the while, PC, PO, PS. And in this case, we're starting off with a single input I, and we're going to start now with a triple, three values rather than two, and the values are I squared, I, and 1. And then we're going to gradually, through this step here, we're going to subtract 1 from the I squared, so just kind of reduce that down by 1 each step, but this second value stays the same. and we're going to stop when the first value is equal to the second value. So in other words, the first value here is always going to be greater than the second value. And we're calling CF, which in turn calls GF, on the first value and the second value. In other words, the input to GF will always start off sorted with this one greater than this one. Helpful to know. And then because of this sort, it stays that way forever after. So whatever output we get here from the stack, we're going to sort them so that the bigger one comes before the smaller one. So we've got I and J, and we're going to subtract J from I and stack that with J. And then if that flips the order, then we'll flip it. So what does that mean? It means we're going to keep subtracting J from I until this number ends up smaller than this number. So what does that mean? Well, just think about a concrete example. Let's say there are numbers start off as, I don't know, 107. So you've got 100 here, 7 here. So you're going to subtract 7 from 100. Now you've got 93, 7. Okay, that 93 is still bigger, so you subtract it again. Now you've got 86, 7. Then you've got 79, 7. Then you've got 72, 7, 65, 7. You're going to keep doing that until this value, before the sorting, ends up somewhere between 0 and 6. In other words, until it is less than 7. And it'll always end up between 0 and 6 because you're only subtracting 7 at a time, which means it can't jump from being at least 7 down to being negative. So you're basically going to keep doing that until you've subtracted as many multiples of this one as you can from this one. And again, your math alarm might be going off here if you know the area. So in this case, we're going to subtract as many 7s as we can from 100, and that's going to leave us with 2. So then our output here is 2, 7, and then the sorting is going to turn it into 7, 2. So then we're going to start the process again with 7 and 2. So again, we'll subtract as many 2s as we can from 7. So we'll go 7, 2, 5, 2, 3, 2, 1, 2. And then at the point where we get to 1, 2, we flip them around again. Now we've got 2, 1. And then we're going to subtract 1 from 2 until we get 1, 1. Now they're both the same. We're going to subtract 1 again. Now we get 0, 1, sort it to get 1, 0. And now we've met the condition for the second value being 0. And so we return 1. Now, if you're not familiar with the greatest common divisor algorithm, then it might not be immediately obvious what that means. But at this point, you know, if that doesn't mean anything to you, you could always try experimenting with some values. So let's say if we try 24, for example, it gives us 4. 25 gives us 5. 26 gives us 2. Play around with it some more, get a feel for it. You'll eventually figure out this GF function is returning the greatest common divisor of the two numbers that it starts off with. So this process where you repeatedly subtract off multiples, the only case where that ends in 0 is where one of the values is a multiple of the other. And then if you kind of work backward from there, you can see what you're taking off. You're always subtracting a multiple of the greatest common divisor of the two numbers. So very elaborate process again, lots of obfuscation going on, but all of this G stuff, the GC, GOGS, is just the pieces to build this G function, which is just the greatest common divisor. So again, we can get rid of all that and just replace this GF with the native GCD function. Wait, I must have missed a name somewhere. Oops. Oh, sorry. No, I missed the name here because I'm still using GF down here. So let's go back to NP of 2025, which it still won't accept, but now it'll not accept it a lot faster. And that's because this next step is still being super inefficient. So what are we doing here? Well, first of all, the CF is just saying GCD ij greater than 1. In other words, I and j have a common factor, and then n of that. So this will return true if the greatest common divisor is greater than 1, meaning that they have a common factor other than 1, because every pair of integers has a common factor of 1. And then n of that true or false will just turn that into 1 or 0. So 1 if they have a common factor, 0 if they don't. So now let's look at what PF is doing. So again, it's a while construction. We're starting off with a triple of the original input I squared, I, and 1. And then we've got a stopping condition, an output, and a step. And so what is the step doing? It's subtracting 1 from the first value. It's not changing the second value. And for the third value, it's adding 1 if the first two values have a common factor. So we start off at I squared and I, and we count down until we get down to, this I always stays the same. This I squared goes down by 1 until the first two values are equal. In other words, until we get to I. And this value that starts off at 1 counts up by 1 every time there's a common factor. And again, your math alarm might be ringing at this point. If there's a common factor, good chance we're thinking about primes. But let's look at one more thing, which is the stopping, sorry, not the stopping condition, but the output. So at the end, by construction, this is always I, and then 1 plus the number of numbers between strictly greater than I and up to I squared that share a common factor with I. Now, if you take a second to think, every multiple of I, other than I itself, between I and I squared, obviously shares a common factor of I, because it's a multiple of I. And so you will always have at least I minus 1 numbers in that range from I plus 1 to I squared that share a common factor. And you start off with 1, you add at least I plus 1, which means that you end up with at least I. So now what is this output condition? It's saying take the unique of I, and this 1 here means by column. In other words, rather than looking down the rows, we're looking across the columns. So we're applying this on a triple that is I, and a number that is at least I. And the question is the count of that equal to 1? If it is, we're returning true. If it's not, we're returning false. So if there are any numbers other than multiples of I that share a factor with I between strictly greater than I but up to I squared, then we're returning false. And if there are no other numbers that share a factor, we're returning true. And again, math alarm ringing at this point. That is, it's a convoluted one, but that is effectively a primality test. So if a number is not prime, let's say if it's 15 is 3 times 5, then between 15 and 15 squared, there are more numbers that share a factor with 15 than just the multiples of 15. So for example, 18 is not a multiple of 15, but shares a factor of 3 with 15. 20 is not a multiple of 15, but shares a factor of 5 with 15. But if you try the same thing for 17, the only numbers between from 18 up to 289, which is 17 squared, that share a factor with 17 are the multiples of 17. And there are 16 of those. And again, you start off with a value of 1. So the only way that you end up with this triple being I, meaning there's only one unique value in it, is if the number you started with is prime. So this whole PF function is just saying, is the number prime? And so now, finally, we can look at NP and say, what is going on here? Well, we start off with a number. In this case, it's 2025. We start off with a number. We check if it's prime. If it is, we return n of that number, which is just a function that does nothing in the case of a number. So we just return the number. And if it's not, we apply in, which is just increment, add 1 to the number. So we test if 2025 is prime. It's not. It's a multiple of 5. So we add 1. 2026, we test if 2026 is prime. It's not. It's a multiple of 2. So we add 1. 2027, we test if 2027 is prime. It is. We stop. We return 2027. And so the answer to the question was 2027. That's the answer that it gives. I realize I had written a version that had a vaguely more efficient prime test so that I could actually kind of prove that. But anyway, you get the idea. So the answers to the exam questions were 1, the output is 2027, and 2, the NP function either returns the number if it's prime or returns the next prime up from it if it is not prime. And I will say 2 things. One is almost everybody who answered gave the correct answer, and 2, many more people got this right than I was expecting to. I was honestly expecting the number of correct answers to this would be sort of between 0 and 3, and I ended up with 16 correct answers. So actually, let me just go and give that crew a quick shout out before we talk about the other pieces. So these are the people who got correct solutions: Aditya, Kumar, Derek, Alwyn. A couple of people only put in first names, which I assume they only want to be identified by first names. Ben Gutcher, Bo Ridabon, Christian, Kobe Dombrowski, Curtis Landry, Jeremy Freelove, Julian Lacaze, Malatesh Shetakeri, Michael Jarman, Michael Wilson, Monther Albeck, Patrick Chatin, Peter Bartholomew, and Sergio Trifoletti. So congratulations to all 16 of you. Only one of you can win a ticket, which I'll come back to in a few minutes, but very nicely done. Before I do that, I said I would start off by doing the sort of entirely theoretical approach, but that I would also talk a little bit about some slightly more practical approaches. So the one obvious approach here was to be a little bit more backward engineering about this. So for example, you could say NP of 3. Oh, look, that gives me 3. Okay, what does NP of 6 give me? Gives me 7. Okay, interesting. Let's just, I don't know, hstack sequence of 10 next to map sequence of 10 NP and see what it gives for the first 10 values. I've entered too few. Oh, sorry. Sorry. Forgot to close a bracket there. That runs for a little while, but you can see 1 returns 1. The mathematicians might argue on that one, but anyway, I didn't want to make my prime testing function even more complicated to allow for the fact that it returned true for 1. 2 returns 2, 3 returns 3, 4 goes up to 5, 5 goes up to 5, 6 goes up to 7, 7 goes up to 7, then 8, 9, and 10 all go up to 11. And now, right away, as soon as you're seeing it's returning 2, 3, 5, 7, and 11, there's probably some alarm bells ringing here about primality being part of the game, because I suspect most people recognize the list of prime numbers. But let's say you wanted to go a little bit further and go up to 15. It's going to take a while, but I think it will get there, as far as I remember. And then you can see, okay, yeah, so it's all 11 up until 11, then it's 13 up until 13, then it goes to 17. These are definitely primes. And so I think it's very possible to just not look at any of the inner workings and just experiment with NP for lower values and say, well, obviously he said NP 2025 runs until the end of time, but NP of 4 doesn't. Or you could take an in-between step. You could do the same analysis that we did of, okay, well, this is a while loop. So what is this while loop doing? Well, it's taking an input, which is a number because we're calling it on 2025. It's doing something to it, and then it's either incrementing, well, it's incrementing it by 1 until it passes this test PF. So then you could say, okay, well, what is PF doing? And again, you could, in kind of the same way as I just did with NP, you could say, okay, let's map in PF, and you'd see, okay, so it's, again, the 1 is a little bit of a red herring, sorry, but you see it's returning true for 2 and 3, false for 4, true for 5, false for 6, true for 7, and so on. Again, it's, if you're attuned at all, it's relatively easy to spot that there's something to do with primes going on here, and make an educated guess that, and again, this is where the names come in helpful. Is like, okay, PF, yeah, you're testing for primality, NP means next prime, got it. So I think lots of ways that you could solve this problem without getting into all the guts of it as I walked you through. But couldn't end this task without talking about the way that at least a few people admitted to solving it, and maybe other people solved it this way as well. Some people asked not to be included in the draw because they had solved it this way, although I thought it was fine to do it that way, which is by asking ChatGPT, what's going on here? And what's interesting about this is I got messages from some people saying ChatGPT had no clue what to do with this. I got submitted responses from at least one person who said, I have no idea, but this is what ChatGPT told me and it was wrong. And then I got messages from a couple of other people saying something like, I gave this to ChatGPT and it solved it in like 10 seconds. Why did you set such an easy problem? So this is an interesting one for me. I was a little naive because ChatGPT can make at least a decent stab at this and can certainly give you some helpful guidance. So here's what it gave me when I asked it about it. It said, well, this is a let, fine. It gave a textbook perfect answer on understanding the WH. Like the recursive pattern WH is a lambda function that facilitates recursion. It takes 5 arguments, and it even correctly identified what these, CO and S were kind of standing for. In my head, this was step rather than state transformer, but like condition, output, and state transformer. Nailed it. Indexing was indeed about, extract was indeed about extracting a value from in was indeed incrementing. And then it kind of went off the rails. So it says here SC, SO, and SS, which were the 3 functions to make up the subtraction function, define stopping conditions, output transformation, and state transformations respectively. True, but for what? Don't know. Then it described SF and GS as sorting and filtering, which I guess was taking clues from the name, or maybe from the fact that the sort function appeared in the GCD definition. But not really correct here. Recursively process and build sorted data. No, it doesn't. It subtracts one number from another. Sorts data for specific operations. That doesn't really mean anything, but sure. So it definitely went off the rails here. And then, in a sort of rabbit out of the hat way, because it clearly didn't understand the GCD element here, but then it did say, okay, well, this is prime number detection. This seems really smart, but I don't think it really gets it, specifically because here the output condition says validates unique values for primality. That is not what the unique function is doing at all. So that, like the test of the unique there is the way I set up the triple, it will only have 3 of the same value if the number is prime because of the math and the GCD and blah, blah, blah. I don't think it had understood that at all. So this like validates unique values for primality is just it kind of bullshitting and guessing based on the name, I think. And then it says prime factorization logic, a recursive helper for prime factorization, and NP, the final function to find prime numbers starting from the initial input. And so it says correctly, like it got lost in the middle, but I think it landed in the end. It says the purpose of the function is to compute the next prime number, and it will, start in 2025 and go until it finds the next prime at 2026. Sorry, it actually didn't say what the next prime would be, but that's fine. It said the next prime greater than or equal to 2025. So Harry Gross and I had a few interesting exchanges on this because we were trying to, get a sense of how much it understood this, how much it had just been able to kind of do a really good job of getting hints from the variable names, which I think it did. Like I said, I did intend these to be helpful hints to a person, and obviously ChatGPT is quite good at picking up on that kind of cue as well. But so how much that helped, how much it really understood. So we did a couple of things. One is we gave it a version of this formula where all the variable names were replaced with the names of Disney princesses and the names of fruits and various other things, and that did definitely confuse it somewhat more. But the other thing, at Harry's suggestion, I responded to this reply saying, "Are you sure the NP function doesn't find the largest prime factor of the input?" To which it replied, "You're absolutely correct. After carefully reanalyzing the function, NP indeed finds the largest prime factor of the input rather than the next prime number. Let me explain in detail how this works," and goes on to offer an equally plausible seeming explanation of how the function does something that it absolutely does not do. So, I guess the lesson to the people who said this problem is too easy, you can just solve it with ChatGPT, and the people who said, well, the answer is 1 because ChatGPT told me to, is it is not trivial to tell, if you don't understand the answer to the question, whether ChatGPT is giving you the correct answer. And in this case, it's very good. Like this is a kind of standard topic. It's very good at sounding plausible, even when it is bluffing, excessively interpolating, or just randomly guessing. I will say Harry ran this through O1, the latest model, and it seemed to be a little bit more robust. So when he similarly asked it, "Are you sure that it doesn't just do this?" It gave quite a catty, like, "Yeah, I'm sure. That's not what it does." So at least seemed a little more confident of itself. But even that, without some of the guidance of the kind of helpful names and other things, struggled to really nail it down. And like similar to this one, it did a little better, but like it got up to a point very clear, very crisp in the reasoning, and then it started flailing about a little bit in the dark. So to me, this was super interesting. Like this to me says ChatGPT is a super useful tool for understanding very complicated Excel functions. And this is, more complicated than most of what you'll have to deal with. But you gotta use it with caution because it will just bluster. Anyway, that's enough of that. I want to announce the winner. Okay, I had to record a new ending for this because I tried to get ahead of things by recording the walkthrough last night before things had technically closed. And then afterwards I got one more correct submission from Will Nord. Congratulations, you got in under the deadline. So finally, big reveal, who is the winner? Congratulations to Malatesh Shetakeri. Malatesh was actually a finalist at the last iteration of Model Off back in 2019 as we met briefly in London. So good to see that he is still doing Excel-ish and excellent things. Congratulations, Malatesh, and everyone else. I hope you enjoyed it. No prize for you. That's all I got for today. Thanks for watching. See you next time.